All right, so this is a second video covering optimization problems for AP Calculus. We're just going to do a couple more examples. This one is very geometric. It says we've got an indoor physical fitness room that consists of a rectangular region with a semicircle on each end. The perimeter of the room is to be a 200-meter running track. Find the dimensions that will make the area of the rectangular region as large as possible. I'm going to start this whole problem by drawing a picture, straight off of that first sentence. So it's a rectangular region. Oops, let me go back to not the highlighter. I've got a rectangular region with a semicircle on each end. That looks pretty much like your high school tracks out on the football field look like. So that's something we can imagine. It says the perimeter of the room is to be a 200-meter running track. So that 200 meters is made up of the whole perimeter. Well, the perimeter, I've got these two lengths of my rectangle plus this part of a circle and this part of a circle. Well, if we put those two parts together, they make an entire circle. The perimeter around an entire circle is 2 pi r. And let me label on my picture, there's an r. Now, you may be wondering why I did not include the widths of the rectangle, but if you look at the picture, those widths, those are inside the track. They're like where the end zones of the football field would be outside. So they're not included in the part that we would walk around. So it's just the two circular pieces and the two lengths. So that is a relationship that we've established now between L and R. However, it has nothing to do with what it is that we're trying to optimize. So the third sentence says to find the dimensions that will make the area of the rectangular, just the rectangular region, as large as possible. So area of a rectangle is length times width. So I've got L's, I've got R's, and I've got W's going on here. So where is this W? Well, W is inside of here, and it's also over here. So if you think about it, W is actually 2 radii. So I'm thinking it might be good to make the area equation in terms of R, because W, I could already rewrite W as 2R, and I could take my perimeter equation and I could solve it so that it's L equals, which would put L in terms of R. So if I do that, I would get 200 minus 2 pi r equals 2L. Then divide everything by 2. So 100 minus pi r is equal to the length. So now I'm going to switch colors so you can see everything I'm doing with the area here. My area equation is length times width, and that's what I'm trying to maximize. Well, the length is 100 minus pi r. The width is 2r. So that makes my area formula 200r minus 2 pi r squared if I distribute the 2r through there. So since that's what I'm trying to maximize, and since it's now in terms of just one variable, I'm going to take the derivative of that. So the derivative of 200r is 200. 2 pi is the coefficient. So when I do the derivative of r squared, I get 4 pi r. That's never going to not exist. So I only need to figure out when it is equal to 0. So that would be 200 equals 4 pi r. 200 divided by 4 pi is the radius. You could simplify that to 50 over pi. I'll be honest, I would leave it as 50 over pi. That is an exact answer. We don't like decimal answers. If you have no other choice but to use decimals, don't use the decimal answers until you get all the way to the end of the problem. Because the sooner you start to round, the more inaccurate your answer is going to be. So save the rounding and the decimals until the very end, or simply don't do it. So I got r equals 50 over pi, but look at the end of the problem. It said find the dimensions that will make the area of the rectangular region as large as possible. So they don't even care what the area is. They just want to know what the dimensions need to be. Well, I know that r is 50 over pi. And if you look at the problem, we're measuring in meters. So it's 50 over pi meters. But I need to also say then what the width would be and what the length would be. I would list all the dimensions. Don't leave anything out. So the width is 2r. So it would be 100 over pi meters. And don't forget your units, because a lot of times, especially if this is an FRQ, one of the 9 points will be for having those units in there. And then the length is 100 minus pi times 50 over pi. So my pi's are going to cancel. So my length is that the track needs to be 50 meters long. And again, multiple answers, write them all together, and put them in a box or make them stand out somehow. So if you look at these problems, I mean, the derivative process was not difficult. And in none of these problems really is the derivative process all that difficult. The complicated part of these is finding all of those relationships at the beginning between the L and the R and the W and the parameter and the area and all the different things that you've got going on. So you really do need to slow down and focus and work hard on having it organized and making sense at the beginning, because then the rest of it is usually not too bad. I do want to look at one more. It's another geometry problem, and this is a very common optimization problem about building a box. It says an open box with a square base is to have a volume of 2,000 cubic centimeters. What should the dimensions of the box be if the amount of material used is to be a minimum? Okay, so an open box with a square base. So what I know about this box, and I'm going to do my best to draw it. I know that the base is a square. So this length and this length are the same. However, I need to connect it. I do not know that it's a cube. So the height of the box may be different from the dimensions of the base. Okay, so think about that. And the volume of it is 2,000 cubic centimeters. Well, volume of a box is length times width times height, or b squared h. So there's a way that we've related the b and the h together. But then it says, what should the dimensions of the box be if the amount of material used is to be a minimum? So the material used is what we use to create the actual sides of the box. Now this box, since it's open on top, it only has 5 sides. So one of those sides, we'll call it, and that's called the surface area. So I'm going to make it a big S for surface area. So one of those sides is the base. Its dimensions are base squared. The 4 sides around it are b by h, and that's true for all 4 sides around the side of the box. So those areas would be b times h, but there are 4 of them. So that's your formula for surface area. Notice it has both b's and h's in it. So this volume formula, I could solve it for h equals, and that's probably easier than solving for b, because solving for b would require doing a square root. And then I'd have square roots in my surface area formula, and then I'm doing derivatives of square roots, and that's just not any fun. So if I solve for the h, my surface area formula becomes b squared plus 4b times 2,000 divided by b squared. So I'm going to simplify this stuff at the end here before I try to take the derivative of it. 4 times 2,000 is 8,000. B over b squared is going to leave me with a b in the denominator. Or b squared plus 8,000 b to the negative 1. That is now what I'm going to take the derivative of. So s prime is 2b, and then if I use power rule on this part, I've got 8,000 b to the negative 2, or 2b minus 8,000 over b squared. Now, this derivative will not exist. It'll not exist when b is 0. But logic tell us that I can't have a b of 0 because that would mean that I have no base length. So my box wouldn't even exist. So that's irrelevant. So all I need to worry about is solving for when this equals 0. So to do that, I'm going to take this whole equation and multiply it by b squared to get rid of that denominator. So it becomes 2b cubed minus 8,000 equals 0. Add the 8,000 over. Divide by 2. And b ends up equaling the cube root of 4,000, which is 15.874. And that's measured in centimeters. So now that I've found my base length, let's go up here to the problem again. What should the dimensions of the box be if the amount of material used is to be a minimum? So they don't want to know how much material is being used, they just want to know the dimensions. Well, we've got the B. H, if you look up at the top of the screen there, is equal to 2,000 divided by B squared. So you would evaluate that in your calculator, and you would get 7.937 centimeters. And then again, I had multiple answers. I made sure I put units on my answers. And then I'm going to put a box around them so that they're easy to find. So there's a few optimization problems to kind of get your brain working on how these optimization problems are supposed to go.